Hi guys, happy Thursday. I hope everyone's doing well. Hopefully you have the sheet in front of you that we're going to go through today. If it's not out in front of you, Miss Lucky, you can pause the video and hand it out, and then we'll get started. Okay, I'm just going to work through this as we go. I'll have different times throughout the video where you can pause it, and I'll give you guys a chance to work on some problems. And then you can restart the video once I start kind of revealing answers. Once the video starts playing again. So let's just go through number one. Le Chatelier's principle states that when a system at equilibrium experiences a stress, the equilibrium will shift to lessen the effects of the stress. Okay, so this is exactly what we learned last year. Just restating Le Chatelier's principle to get us rolling for today. Number two, let's list some stresses for things that can potentially affect an equilibrium. A change in temperature will affect the equilibrium. Change in concentration of anything in our equilibrium. And also a change in pressure is another example of a stress. There's more than just these three, and I'm sure you probably can remember at least one of the other ones that we talked about last year as well. If we ever add a pure solid or a pure liquid, the equilibrium will not change, and there's no change in concentration, so therefore no shift occurs. And number four, if a pure solid or a pure liquid is, the pure solids and pure liquids are never included in the equilibrium constant expression. Again, we've seen that, we've been working with that, so hopefully that rings a bell. You just have to be careful, make sure you keep an eye on those little phase tags when we're doing problems, and make sure that if it's a solid or a liquid, you never include it in that expression. Okay, let's try number five here. This is an example of an equilibrium, and we're going to see if we can figure out which way this is going to shift. So if sodium phosphate is added to the equilibrium up here, what color change would we see? Okay, so this is actually pretty difficult to figure out on the surface, but I'm going to give you a hint, and that is that the sodium phosphate that's being added is soluble, but the compound of lead phosphate is not. So why don't we pause the video for just a second, and you guys can give this one a shot. Come back when you're ready, and then you can play, and I'll reveal the answer for you. Okay, so the answer here is that essentially the iron ions and the phosphate ions are going to combine, and we're going to form a precipitate. Therefore, the iron ions on the left side of our original equilibrium are going to get used up, and this thing will shift towards the left. Okay, so the question was asking is what color change do we observe? The color change we're going to observe is that we're going to go from a more reddish color to a pink or colorless solution. Okay, let's try B. Similar type question. You have another equilibrium, and this time we're adding sodium cyanide to this equilibrium. Okay, so kind of like the first one, it's not readily obvious what the answer is going to be. Here's another hint for you. The cyanide from the sodium cyanide that's going to get added is a conjugate base. So again, pause the video please and give this one a shot. When you're ready, come on back and I will reveal what the answer is. Okay, so because that cyanide's a base, in our equilibrium up here, the cyanide's going to react with the hydrogen ion on the right side. Okay, we're going to use up the hydrogen ion on the right side of our equilibrium, and we're going to cause a shift to the right. Okay, so again, that's observing the shift. The question's asking us how the pH is going to change. Well, if we're using up hydrogen ions, obviously the pH will go up. We're going to have a more basic solution after we've added the sodium cyanide. Okay, C, this is an example of hydrogen gas and chlorine gas reacting to make hydrochloric acid. So in this one we are adding hydrogen gas to the system, and we're asked how the temperature is going to change. So please pause the video again, give it a shot, come on back, and then I'll reveal the answer. Okay, so if hydrogen gas is added to this problem, you will be adding things to the left side of the reaction, causing a shift to the right, because our energy term is over on the right-hand side, this will increase, and that increase in energy is going to therefore increase our temperature. All right, D, the last one that I have for these equilibrium problems, kind of just getting this rolling today. If you have a saturated solution of sodium chloride at equilibrium and add more water to the system, which way will this reaction shift? So again, pause the video please, give it a shot, and come on back. Okay, so if we're adding water, hopefully you caught this one, but water is a pure liquid. So, because water is a pure liquid, we can add as much as we want, and nothing will happen to our equilibrium. Okay? So you may be thinking, well, it's on the left side, if we add something over here, it's going to shift right. Hopefully you didn't make that mistake. You add a solid, you add a liquid, the equilibrium won't be affected. Okay, now let's get into some problems from the book. And this is going to kind of introduce the new topic for today, which is Kp. Alright, and Kp is the equilibrium constant for gases, equilibrium using gases. So the general concept is the exact same. The only difference is in your equilibrium expression, instead of using concentrations, you're going to be using pressures. Okay, so this first example here that I give you has pressures in atmospheres. Sometimes they will be in torr, sometimes they're in millimeters of mercury. It doesn't really matter the units of pressure we use as long as we're consistent with what's in the expression. Okay, so let's read through this problem. We have the following pressures observed at equilibrium. We have hydrogen gas, nitrogen gas, and ammonia, and we're asked to calculate the equilibrium constant Kp at this temperature. Okay, so I have a little PS down here. You should always write a chemical reaction even when you're not told to do so. A chemical reaction in this case is going to be extremely helpful. So pause the video, try to write the chemical reaction first. Once everyone's got the reaction, come on back and I'll reveal it and we can keep rolling. Okay, so the reaction you should have gotten here is like this. Okay, we're going to have 3 moles of hydrogen gas reacting with nitrogen gas, giving us 2 moles of ammonia. Okay, and the reason why that's important is because if we want to find Kp, we have to set up the appropriate equilibrium expression. So, with that said, try setting up the Kp for this reaction. Products over reactants as always, so hopefully this makes a ton of sense and is not too bad. Pause the video and give it a shot. Okay, so you should have gotten this expression right here. Alright, so different from our normal equilibrium expressions, you'll see that I have P, which stands for pressure, and then I have the chemical subscripted. So again, products, the pressure of ammonia, squared because of our coefficient right here, over our reactants, pressure of hydrogen, to the 3rd power because of the coefficient, and the pressure of nitrogen. Okay, so now that we've got the perfect setup, go ahead, take those numbers, plug them in, and let's actually solve for our value of Kp. Here's what the setup's going to look like. Give it a shot, plug it into your calculator please, pause the video when everyone's got it, come on back. Alright, so the answer you should have gotten here is 3.8 times 10 to the 4th. And again, this is just a generic set up the problem, a reaction using gases, set up a Kp, plug in the numbers, and solve. Hopefully that was relatively straightforward. Let's go to B for question number 30. B is giving us an example of different pressures using the exact same reaction. So the reaction we want to use is still our hydrogen gas plus nitrogen gas giving us ammonia. But now we're at an instance where we're no longer at equilibrium. So instead of setting up a Kp, we would set up a Qp. Alright, so I've talked about K and Q quite a bit. And just to refresh you again, K and Q are set up the exact same way, products over reactants. K is when our system is at equilibrium. Q is at some other point in time when we are not at equilibrium. Once we solve for our value of Q, you can then reference K, and depending on whether Q is larger or smaller, you will then be able to determine which way the equilibrium should shift. Okay, so there's our setup. We've got our values up here in the problem. Plug them in. Solve for this, please. Pause the video and give it a shot. Come on back, I'll give you the answer, and then we can talk about why it shifted the way it did. Okay, so the answer you should have gotten in your calculator is 1.21 times 10 to the third. Once you solve for Q, you do want to go back and you want to reference that against your K value. So K, from the previous example, was 3.8 times 10 to the fourth. So if we compare our Q to our K, Q is larger than K. Therefore, we're going to shift to the left. Okay, we have too many products at these current conditions. So our equilibrium will shift towards the left. Okay, 69. This is an example of a reaction that you've never seen before. I give you a couple hints of setting this up, but we're talking about ammonium carbonate, which the formula is given to you here in the problem. And I'm asking you to just try to set up a reaction for the decomposition of ammonium carbonate. The hint here is that you're going to get ammonia gas, and then you're going to get two other products. Those two products are gaseous products from hydrocarbon combustion. So if you remember what a combustion reaction gives us as products, hopefully you can figure out the other two. Pause this for just a second and come on back and I'll show you the answer. Okay, so the reaction should be our ammonium carbonate breaking apart. We get the ammonia gas, we get water vapor, and we also get CO2. Okay, so now let's use that. All right. In 69b, we're told that this reaction is endothermic. So if we want to include an energy term on our reaction, we should include that on the reactant side. Okay. Endothermic means we're putting energy in. The energy term should show up on the left-hand side. As temperature increases, the smell of ammonia would increase, because if we are adding energy, our energy term is on the reactant side. An increase on the left-hand side of our equilibrium is going to push it to the right. Ammonia gas is a product on the right-hand side, so as we shift right, we see an increase in that smell of ammonia. Okay, the last one here is referencing the table underneath the red box that I have right here. So please pause the video, read that question, and see if you can cross out the appropriate temperature scale on the right-hand side. One of these would represent an exothermic, one would represent an endothermic reaction, so hopefully you can interpret the data and figure out which one makes the most sense. Please pause the video. Okay, so here's the answer. We should have crossed off the very first set of temperatures, and the reason is if we increase the temp, so I'm kind of tracing from the bottom up to the top here on the correct scale. If you increase the temperature, we're really increasing the energy term on the left-hand side of our reaction. If we increase the left-hand side of our reaction, we're going to shift to the right and get more products. So as temp goes up, we should expect to see an increase in K. I hope that makes sense. Have a very good day, guys. You can now work on your homework for the rest of the hour. If you have any questions, please feel free to post on that discussion board. I'll try my best to answer that. And then tomorrow when baby is born, I'll try to post a picture on there maybe too. Have a good day.